Okay, so I want to conclude the sections on bundle theorem with focusing on vector bundles because those are the ones that we will be interested in most. And last time we already saw that connections of vector bundles have some specific properties. So the covariant derivative of satisfies certain Leibniz rules and linearity, and this is because of the fact that we ask parallel transport to be a morphism in the corresponding category. Now there is curvature in case of a vector bundle. So let's say, so the setup is as follows. M is a differentiable manifold, and F is a C bundle over M, where C is one of the categories of linear vector spaces. So that might be one of the following categories. Could be real vector spaces of some dimension, or complex vector spaces of some dimension, or it could be Euclidean vector spaces of some dimension, or Hermitian vector spaces of some dimension, or it could also be an oriented vector space of some dimension, so real, and it could be also Euclidean and oriented. So those are basically the ones we are interested in. So this corresponds to real vector bundles, complex vector bundles, Riemannian vector bundles, Hermitian vector bundles, oriented real vector bundles, and oriented real Riemannian bundles. Okay, and let's furthermore assume we have a connection. So let H be a connection, C connection on the bundle with induced covariant derivative nabla. And in fact, I want to consider nabla really as a map that maps sections of the bundle to sections of the bundle itself. So I'm using this convention and not to the vertical bundle, but we have seen that this is canonically identified. So convention that we are going to use for simplicity. It's not really necessary. For simplicity, I want to use that for any section S. This is a section of my bundle, and X attends to the vector field. Then nabla takes S as again a section of the bundle. While we remember in general it's a section of the vertical bundle, but in the case of vector bundles it can canonically be identified with the bundle itself. Alright, and then there's the usual formula for the curvature tensor. So for two vector fields, X and Y, and a section so we put R, X, Y, right to S by applying the covariant derivative twice. And there are two orders in which we can do that. So first differentiate in direction S, then differentiate the resulting direction first in Y, then in X, or we do it the other way around. Take the difference, and then there's a correction term taking care of derivatives of the vector fields, which is the covariant derivative of S in the direction of the vector fields. And and that's why it's convenient now to assume that this is again a section in the same bundle, because then we can repeat, right? Then we can apply the covariant derivative repeatedly. So that is another section in my bundle. And then one checks that this is actually that the result of this section at a certain point depends only on the values of x, y, and s at that point. Okay, so R, x, y, s evaluated at a point P in my manifold M depends only on the values of x at P, y at P, and s at P. And in fact, this is the reason why we subtract the 3 bracket part, because otherwise we would get also derivatives of x and y at P, which we don't want. And you certainly know this, the argument that leads to this, so I won't repeat it here. So what you check is that if you insert functions in front of these vector fields in the section, then it turns out if you use the rules that we have obtained for the covariant derivative, that all derivatives of the functions at a given point cancel out. And this then implies that the result depends only on the values of x, y, and s at that point. So in other words, this is really a tensor. So R is a tensor field on my manifold. So this implies R can be considered as a section on my manifold. Now, what's the bundle it's taking values in? If I insert fixed vector fields s and y, then I get a section in my bundle F. But if I leave x and y open, then this is bilinear in x and y. So we get a T star co-tangent bundle tensor itself, but it's also anti-symmetric in x and y, because if you interchange x and y in this formula, you get a negative sign. So it's really a 2-4. So therefore, we can consider this as a section in two forms on M tensor. Tensor F, well, this is when I insert a fixed S, but if I let S open also, then of course I get an endomorphism from F to F. So unfortunately there's a little too little space here, so this is tensor endomorphisms of F. So endomorphisms is a smooth functor, so we can apply this to the bundle and get another vector bundle. All right, so that is my curvature tensor. And you certainly have seen this in differential geometry 1 course, at least in the case when this bundle is the tangent bundle itself. And in order to construct our characteristic classes, I need to write curvature and connections in a slightly different way. And this is done using local trivializations. And this is as follows. So first of all, we observe that local trivializations of bundles correspond, so our bundle is fixed, so local trivializations, or yeah, if I have a local trivialization, phi, this is defined in some open set U, and and then maps points in U to phi x, which is isomorphisms from fiber at F to the model fiber. Right? So that's a local trivialization. If I have that, and let's say in our case, as my model fiber, of course I could use any n-dimensional real or complex vector space here, but I can also choose a specific one, since they're all isomorphic, namely Rn or Cn. So maybe I should have added this here. So this is with model fiber. Kn, where k is real or complex numbers. So this is my model fiber F. Good. So if I have such a local trivialization, then I can associate to this sections in my bundle, which are defined only over U, by taking elements, fixed elements in F, so in Kn, and going the trivialization backwards. So from this, I can associate. So remember, this is Kn. So now I take the standard basis of Kn. E1 up to En is the standard basis of Kn. So I take one of these standard basis vectors and I put Sj of x equals, let's take Ej, the jth basis vector, and let's apply the inverse of the local trivialization to it. Then this gives me an element in the fiber fx in here. So this defines a section over the set U, a smooth section, because this is smooth. And I can do this for every j. So I get a whole bunch of sections. So I get this set of sections from j from 1 to n. And now at each point, so these sections, they are smooth sections defined over U. So it's a smooth section of the restriction of my bundle to U, right? And each Sj. But moreover, since these are basis vectors and these are linear isomorphisms, in our case for vector bundles, then these are basis vectors for each x. So that's the crucial thing. So for each x in U, S1 of x up to Sn of x is a basis of the corresponding fiber f of fx. So each element in the fiber can be uniquely expressed as a linear combination in these vectors. So given a local trivialization, I can take the standard basis of Kn and make out of this local sections, local basis, which depend smoothly on x, at least over the same set where this local trivialization is defined. Conversely, if I have such you call this a local frame, right? So this collection of sections which form a basis at each point is called a local frame, defined over U. Local frame defined over U. Conversely, if I have such a local frame, meaning I have sections defined on U, smooth, and at each point they correspond, at each point they give me a basis, then I can define the isomorphism phi in such a way that the standard basis gets mapped to this basis S1 of x up to Sn of x here. So this then uniquely defines phi x. So if I have such a local frame, I get this local trivialization back. So this is a one-to-one correspondence between local trivializations and local frames. In fact, if this is the category, if the category is, for example, Euclidean spaces, then we would know that then the standard basis is an orthonormal basis, and the isomorphisms are morphisms in the category of Euclidean spaces, so they are isometries. Then this would tell us that these smooth sections are not just bases, but they are actually orthonormal bases. And similarly for the Hermitian case. And in the oriented vector space case, we would know that this basis is a positively oriented basis. So this structure will always be preserved. So maybe I like this here. Orthonormal if the category is Euclidean spaces or Hermitian spaces. And positively oriented if the category is oriented vector spaces. Or, yeah, oriented Euclidean spaces. This oriented Euclidean spaces applies here too, of course. And then, of course, I need to start with a local or the normal frame in order to get a local generalization for my bundle back, for instance. Okay, so that's just doesn't really matter whether we talk about local generalizations or local frames that are local frames that correspond to the structure in the category. So being a basis plus possibly also normal plus possibly positive oriented for these categories. So that now means that we can also express curvatures and connections in terms of such bases, at least locally, where we have these bases and generalizations available. So let's work with such a local frame, and so what I can now do is for a tangent vector to the manifold where the point P lies in this set where my frame is defined, or my generalization is defined. There I do the following thing. So I take the ith local frame and I differentiate it in direction x with my covariant derivative, and this then gives me an element again of my fiber f at the point P. Right. So that means the result can be expressed as a linear combination of these basis vectors of these bases here at P. So I can write this as, this defines the right hand side, a linear combination of Sj of P with certain coefficients. And the coefficients depend on I and j, of course, but also on this vector x that I have inserted down here. And so let me call the coefficient little omega of x ji. And this summation is over j. So this defines these coefficients here. So these are numbers, real or complex numbers. Okay. So this defines these coefficients here, right? So now, since I have these two indices, I'd like to consider them as matrix entries. So this is now an n by n matrix with real or complex entries. And for each tangent vector, this depends linearly on x, right? So the covariant derivative in the vector bundle case is linear in x. So that also means that these coefficients depend linearly on s. And this means that these entries in the matrix, if I leave the x slot open, are actually one forms. So we have x to number x as I is linear, linear. Therefore, omega, which is just defined as the matrix of the omegas where I leave the x open, this is now a matrix where the entries are linear forms on TPM, but P can be any point in my set U, so they are one forms on the set U. So matrix, an n by n matrix, where now the entries are 1/4. And this is defined over U. So that's the connection matrix. So omega is called the connection matrix. Of my covariant derivative of nabla with respect to this frame, with respect to the local frame S1 up to Sn. Okay. Now, we have these different types of vector bundles, and they correspond to different structure groups. So let me recall this. So if we have the category C here, so let me make a table here, then we have a corresponding structure group. So what's the structure group? This was isomorphisms in the category from model fiber to model fiber. Right? So that was the definition of the structure group. And so in the case of vect n, Rn, here the structure group was just linear maps from Rn to Rn, so this was GLN. In the case of vect Cn, this is the complex linear group. So the real case, I just leave out the coefficients, but there's no coefficients in the real case. And then in the Euclidean case, so then we have isometries from Rn to Rn. So that is On. And in the oriented or Hermitian, then I get UN, unitary matrices. Then I have the oriented case, which gives me the GLN plus. So those invertible matrices with a positive determinant. And finally, the oriented Euclidean case gives me SON. So those are the important ones. And now all these groups that we have here for this vector bundle, they are all finite dimensional, first of all, right? In general, that's not the case for fiber bundles. For example, the structure group is just a diffeomorphism group, but here they are finite dimensional. They are actually all Lie groups. In fact, they are all subgroups of GLN or GLNC. They are matrix subgroups. And corresponding to each Lie group, there is a Lie algebra, which is somewhat simpler to deal with in general. So let me call this structure group, we called it G. And then there's the corresponding Lie algebra, which I will denote by this German little g. And how is the Lie algebra how would that be defined? Well, if since G is a sub, in our case, G is always a subgroup of GLN, or which would be sitting in all n by n matrices, reals, or it's contained in the complex group, which is contained in complex n by n matrices. So both they are submanifolds in either this space or that space, and these are linear spaces, right? This is r to the n squared, this is c to the n squared. And so what I can do is just take the tangent space of this, so the identity is always, the identity matrix is of course contained in it, and I can take the tangent space, this and I can consider it as a linear subspace of this or that matrix group. So G is defined to be the tangent space of capital G at the identity matrix, and then considered as a subspace of n by n matrices with coefficients in R or C. Just write K here. And so in other words, in order to get all the elements in here, what you need to take, you need to take curves in your group G going through the identity and differentiate them. And then you get all the matrices here. And this is then a linear subspace, right? So this is not a linear subspace, but this is a linear subspace. It's a tangent space contained in this linear space. So what would be the Lie algebra corresponding to the first one? All of that. And here similarly, of course, we have then all n by n matrices with complex entries. And now here, what we do get here? We get what's we would now write as O of n, but what is it? What kind of matrices are these? If I have a curve of orthogonal matrices and I differentiated the identity, what kind of matrices do I get? So here this is real. In the real case, there must be some subspace of reals here, right? Matrices A, n times n real matrices satisfying some condition. What's the condition? Skew symmetric. A transpose is minus A. Exactly. And similarly, in the case of un, we get a little un, and those are the complex matrices for which what is true? This looks good, right? And then GLN plus, what is it? It's again this one, for the same reason. In this case, we have the pre-image of all positive numbers. Yeah, so that's still open, still an open subset containing the identity. So we get as our tangent space all matrices with real entries. So same Lie algebra is here. And finally SON. Yes, exactly. All right, yes. Okay, good. Why am I mentioning this? Because I'm talking about this, this connection matrix, and the fact that this matrix is coming from a C connection should somehow reflect in the structure of that group that I get here, and that's in fact true. Namely, it turns out that the matrix that we get this way is always contained in the corresponding Lie algebra. Okay. So we'll call this a lemma. The matrix omega of x is contained in the Lie algebra for all x tangent to my manifold n, where p runs through the set U where the slope frame is defined. Okay, and so why is that? Well, so somehow we must use the fact that our connection comes from something, so that parallel transport is always contained in here by definition, and the things that we get here we get by differentiation. And this is the definition of the Lie algebra. On the other hand, the covariant derivative also is somehow obtained by differentiating parallel transport. So this should set up the relation. Okay, so let x be such a tangent vector. And then let's choose a curve representing x. So let c from some interval to m or to u, we can just restrict it to stay in u, be a smooth curve with c of 0 equals b and c dot of 0 equals x. And now we know that the covariant derivative in direction x of Sj was defined to be the derivative at t equals 0 of what? Take the section at the curve point C of t, then this gives me an element in the fiber at C of t, parallel transport it along the curve C from t to 0 to get a curve in the fiber over C of t 0 and then differentiate. And then we also have this natural identification of the corresponding vertical vector with an element in the fiber of f itself. Maybe I should call this iota p, I think we called it. All right, so that's the definition. And now this section, where's the definition of the section? We still have it here. Let's insert this. So this is iota p ddt at t equals 0, parallel transport from t to 0 of, and here we have phi to the minus 1 at c of t applied to ej. That's what we have on the one hand. On the other hand, we have this definition of the curvature matrix. So on the other hand, we have this formula. Maybe I should have called this SI. I and I here. On the other hand, we have this, which is sum j from 1 to n as coefficient, and then by definition I have phi at c of 0, which is p to the minus 1 of j. And now this thing is a morphism in the linear category, so that's a linear map. So I can equally well push the coefficients in the sum inside. So I can also write this as phi that's 0 to the minus 1 of sum j equals 1 to n, these coefficients times ej. And now we compare the expressions that we've got, and we see that this sum inside is equal to, I put the phi to the minus 1 on the other side, composed with ddt t equals 0 of parallel transport from t to 0 of phi ct of ei. That's what we have, right? What does this mean? Well, this means that this matrix is the representing matrix of an endomorphism of Kn, namely the one that we get by taking this composition, and it's a representing matrix with respect to the standard basis. So let me just write it down. So therefore, omega of x is the matrix representing what map? Well, it's this map that we have here. So it's the linear map phi c of t to minus 1. So there's no minus 1 here, and there's a minus 1 here. Sorry. Minus 1 p t0 of c differentiated at t equals 0, then followed by this natural identification isomorphism, and followed by phi at c of 0. Indeed, this is an endomorphism of the model fiber, because phi to the -1 goes from the model fiber to the fiber over this point. Parallel transport takes me to the fiber over C of t, do an identification with the fiber of the bundle itself, and then go back to the model fiber. So that's an endomorphism of the model fiber, which is Kn. So it's an endomorphism of Kn. And this is represented by this matrix. This is what this formula here says. But so these are two linear maps which actually do not depend on t. So I can push the derivative outside also. And then I have phi c of 0 composed with iota p composed with parallel transport composed with phi c of t to the -1. And all this is differentiated. Okay. And now that's good, because the local trivialization consists of morphisms in my category. So that's a morphism in the category. Parallel transport is also a morphism in the category, because this is how we defined connections. And this identification is a morphism in the category, and that's again, local trivialization morphism in the category. So in other words, this is a morphism in my category from model fiber to model fiber. Isomorphism, actually, of course. The model fiber is Kn. So that's nothing but my structure group G. And so we have a curve in my structure group G, which we differentiate, and this gives me exactly the vectors in the algebra. And so, therefore, the whole thing, after differentiating, is an element in the algebra. And that's the claim. So we can now think of this connection matrix. So it's gone, I guess. We can think of the connection matrix in two ways. Either we think of it as a matrix where all the entries are one forms, or we think of it as a G-valued one form, where G is the Lie algebra of the structure group. But it's always only defined locally, because we needed this local trivialization in order to get the local frame and in order to define it. Okay? Good. All right, then you can play the same game with our curvature. So we fix two vectors x and y and apply this to Si. And again, at the point P. And again, I can, so x and y are tangent vectors at the point P, P and U. And I can also express the result, which is again in the fiber Fp, in terms of the basis. So I can write this as sum certain coefficients times Sj at P. And the coefficients that come up this time, I call capital omega, Ji, and this time they depend on two vectors. So we got this. And yeah, so now curvature, that's the curvature form of a omega, or let's say this thing is linear in x and y because the curvature tensor is, and it's also skew symmetric because the curvature tensor is. And so these coefficients that come up here, if I leave the slots x and y open, are two forms. So then we obtain these two forms. So there are two forms defined on this open subset. And yeah, that's what they are. Restricted to U, or the cotangent bundle of U, if you like. So we get this bunch of two forms, we get a matrix of two forms. And this is then called the curvature matrix. With respect to this local frame. Or generalization phi, if you like. So that's similar. Now we have an n by n matrix here, but this time the entries are two forms rather than one forms. And in fact, there's a nice way to compute the curvature matrix directly out of the connection matrix. That's what we want to see next. Structure equation. Position. There are two statements. Let me first just concentrate on the structure equation, which is that omega can be computed out of the connection matrix by this formula. So what does this mean? So I mean, both capital omega and little omega are matrices. And here the entries are one forms, here the entries are two forms. Now applying the differential to such a matrix of forms just means I apply the differential to each entry. So this will then give me an n by n matrix of two forms. And this term, if I have a wedge product of, this is not just a form, it's a matrix of one forms, right? So this means matrix multiplication, where all entries are multiplied using the wedge product. Okay? And that's also a reason why, so this general, if you had one form and you wedged it with itself, it would give you 0. But that's no longer true if it's a matrix of one forms. Okay. So that's not a that's general and non-trivial contribution. So proof. And there will be a second statement in a moment. Okay, so well, let's compute it. So where's the definition? So let's start from this definition. So we have this. Okay, maybe before I start the computation, I'd like to make a certain simplifying assumption. So these are the x and y's are tangent vectors at P. In order to apply the definition of the curvature tensor, I need to extend them to vector fields near P. And I want to do this in a smart way to avoid unnecessary complications. I'm going to do extend x and y in such a way that the covariant derivatives of them at P vanish. And in particular, the leaf brackets vanish. So let's extend x and y to vector fields defined on U. I could work with any extension in principle, but it's convenient if I do it in such a way that at the point P, the leaf bracket vanishes, such that the leaf bracket of them at the point P is equal to 0. Then these leaf bracket terms will drop out. And this is always possible. For example, if you give the manifold a Riemannian metric, then you can extend the fields in such a way that the covariant derivatives of x and y vanish at that point P by just taking x and y and parallel transport them along radial geodesics emanating from the point. And if the covariant derivatives vanish, then the leaf bracket will vanish too. But here we did not start with a Riemannian manifold. That would just be an auxiliary device to construct an extension with this property. We could, in principle, yes. So if both vectors are linearly independent, we can choose local coordinates in such a way that they are two of the coordinate fields. And then we just take that extension and we will have that. And now, of course, you also might have that y is a multiple of the other one. Then you can extend in such a way that y is always the same multiple than the other one, and then this will again hold. Yeah, that's another way to do that. Many ways to do it. And that's why I'm not writing it down, I'm just saying that it's possible to do that. Alright, and it's also not necessary to do the computation with this assumption, but this will avoid certain terms which we cancel out in the end anyway. Alright, so now let's see. So we have this curvature applied to SI. So I'm doing the computation now at P, but I want to avoid inserting the point P to not make the notation unnecessarily complicated. So on the one hand, this is the definition of these coefficients, right? So this is sum omega of x, y, SI. There's now here, this is j. We have some over j. And on the other hand, I can insert the definition of the curvature tensor. So this will give me nabla x, nabla y, SI minus nabla y, nabla x, SI. And SI. And I don't need the lead bracket term because of this. I do the computation only at P. Yes. Ji. Thanks. And now I insert the definition of the connection forms here. So I get nabla x of. And here I can write this now as sum of the little omega of y. Now this becomes an sk, and the coefficients are k and I, and summation is k, minus the other way around. And now let's differentiate once more. We know that the covariant derivative is linear, so we can drag the sum out, and we know that there's a Leibniz rule, so when we differentiate this function times this section, we have this Leibniz rule. So we get summation over k. Then we have first to differentiate this part here. So that's a function. So that's the derivative in direction x of this function times the section plus this function at p, of course, times the derivative of the section. That's what we get from the first term, and similarly the second one where we interchange x and y. So minus, just have to interchange x and y here, and another minus, and another minus, k, and another minus minus this one with y and x interchanged. Okay. Maybe I'll continue here. So let's first combine the first and the third term. So this gives me the sum. So if I just copy it, I have del x omega y ki minus del y omega x ki sk. And for the second and the last term, I have to repeat this procedure and again insert the definition of the connection form. Then this gives me sum over k, and then, so let's start with omega of y ki, and now I have to replace the covariant derivative of sk with respect to x, which gives me an omega of x. And here we have k. There's now a new index L. We call this SL, so this is double summation over k and L. So that's this one, and similarly for that one with x and y interchanged. Minus omega x, ki, and y, and k SL. And maybe I rename the summation index in the first part to L so that we always have an SL here. Then I could combine the two. Okay, now what have I got here? So the first term is really the exterior differential of omega evaluated on x and y. Because this is the formula, there's another term missing which contains omega of the E bracket, but that's zero. We'll consider it. So this gives me this exterior differential of this one form on x and y. And for the second part, we have, see, if you look at this, this looks like matrix multiplication, except that the parameter with which we multiply vectors is the upper one. So we need to really interchange the two to get the matrix multiplication. And then the first, so then we get, how should I say? Then we get, for the first part, we get plus omega. No, this is exactly matrix multiplication, and this is then multiplied against the vector. So this would give me omega of y, wedge, omega of x, and these are the indices Li here. So multiplied. And that's the same as saying it's a wedge product where I leave this open. Okay, one step after the other. This is omega of y times matrix multiplication omega of x with indices I and L. And so here we have the opposite order. It's not commutative because it's matrix multiplication. Right? Li, and the whole thing multiplied with this line. Yes, X, sorry. Okay, so the first thing is already what we want, and now here we have, this is exactly the wedge product. Statement, but this gives me sum over L. The first thing is just the omega of x, y, Li, and the second part is now minus, if I want to want to have this order, minus omega wedge omega evaluated on x, y with the indices y multiplied by SL with SL. And now if you leave x and y open, this is exactly the statement that we had on the board. That omega is equal to d middle omega minus omega. Right, so if you have the connection matrix, that's one way to compute the curvature matrix out of it. Now, if you think back of Riemannian geometry, where what would be the information that is contained in this little omega? If you use, let's say, local coordinates, for your local frame, for your local polarization. How do you have to think of the entries in the little omega? Christoffel symbols, but the Christoffel symbols have 3 indices, right? Whereas these ones have only 2. Yeah, so the vector x that you insert, if you inserted a coordinate vector del I into it, then you get exactly the Christoffel symbols, gamma I, jk. And jk would be then the entries in the matrix. So essentially, it's the Christoffel symbols that are the little omega. And there's a prescription how to compute the curvature entries out of the Christoffel symbols. There's one term where you have to differentiate the Christoffel symbols, and there's a quadratic term in the Christoffel symbols. All right, good. And another thing is the so-called Bianchi identity. And that's the statement that if we differentiate once more, take the differential of the curvature form, then we get omega wedge little omega minus the other way around. But that's now relatively easy once we have the first equation. So let's see, if I just use the first equation to compute del omega, then I get del little omega minus del omega wedge omega. Now this is applying the differential element-wise, and so del square is always 0, so this first term is 0. This does not contribute. And here we have minus d omega wedge omega plus omega wedge d omega. And so now for this part we can again use the first equation and solve for this. So what we get is it's on that side, that's on this. So this is minus omega wedge omega. And similarly for the second term, plus omega wedge. And now I have this one, which is omega minus this one. And so we see that the triple little omega part comes up here and here with the minus sign, and here, now here should have been with the plus sign. Here it's a plus sign, right? If I bring this.
No, the second one is plus.
This one is plus. It's if I bring this on that side, so here it's a plus. Yes, thanks. So in any case, they cancel. No? So this and that part cancels. And then we are left with minus omega wedge omega plus omega wedge omega. So it's the opposite side, right? So it's like this. Okay. That's it. So that's the so-called Bianchi identity. Good. And so I told you that the curvature matrix takes its values in the Lie algebra. How about the curvature matrix? So as a corollary, we note that omega of x and y is also always contained in the algebra. It's also g-valued, but it's g-valued 2 for this time. And why is that? Well, so here, so we use this this first equation here. Now, so this is d omega x and y. Now the little minus the other term. This thing, so that omega takes its value, little omega takes its values in g. Now I apply this differential operator to it, element-wise, and then if little omega takes its values in the linear space and I apply the linear differential operator to it, then this will be again in the same linear space. So that is certainly G. And how about the other term? Well, the other term I could also write as follows, namely, this I could also write as the Lie bracket of omega x with omega y. Unfortunately, I erased the formula. I had this formula that you have omega of x blah blah times omega of y minus the other way around. So that's this Lie bracket. And this linear subspace G is not just a linear subspace of n by n matrices, it's a Lie subalgebra, which exactly means that it's closed under taking Lie brackets. So this is also in G. And so that's the proof. Good. Okay, so we have that. And that's this thing. Now one may ask, how do these things change when I change the local trivialization? And this is, for the curvature matrix, this is simpler than for the connection matrix. And the reason for this is that the connection is not a tensor field, whereas the curvature is a tensor field. So this represents a tensor field, while little omega doesn't. It represents a connection. And this makes the transformation properties of the capital omega simpler. So let's see, let phi and phi tilde be two local trivializations. Over u and u tilde, respectively. And we can compare them only over the intersection, of course. And so what we have is now the transition map between them. So the transition map is defined on the intersection, and it maps P to the composition phi tilde to the -1 at P composed of phi at P. So this goes from the model fiber to the corresponding fiber in the bundle, and then back to the model fiber. So this is, since these are morphisms in my category, this will be elements in my structure group G. So it's a G, it's a function on this intersection with values in the structure group, this transition map. Okay, so let me call this map T. So, T of P for transition. Now, does my curvature matrix transform? All right, so as I of P is given as, well, take phi P to the -1 applied to Pi, and similarly Sij of P is the same with the other trivialization. And so if I want to express the tilde frame in the untilted frame, then I can insert, I should maybe do it in the other way around. I express the tilted frame in the untilted frame in the tilted frame. Then because I want to get this transition now, then this is, no, sorry, this one. Because then, so I have phi tilde to the -1 P, and now the EI I can write as phi pi, so apply the inverse of this, to Si of P. Alright, so that would be, well, not quite, because the point is, You know, this maps Kn to Kn, whereas here I want to map things from one fiber to the fiber. Anyway, so let me start like this. I express the tilted one in a linear combination of the untilted ones. I can do that, and let me just call these coefficients Tij for the moment. So at P, and we'll relate it to this in a minute. And now I can compare my coefficient matrices. So I have R, X, Y of S tilde, which by definition is the sum of omega tilde X, Y, S tilde J. Now this is R, X, Y, and here I can insert this sum. By linearity, this is sum of here, yes, of R, X, Y, S, J, and this can express in terms of the omegas. So this is sum J, sum over K, and then I have Tji omega of X, Y, I, K, S, K, right? And on the other hand, this can be expressed in terms of the untilted frame too. So then I would get sum over J, and it's the second sum, which is by this formula Tji times, maybe not J, it's a K, Sk. Like this. Okay. There's some index wrong, that's a J. Right. So what will if I compare, then I get that this matrix multiplied by the matrix containing the t's is equal to that matrix, and here the multiplication, and here it's the lower arm. There's also something wrong here. It's a J here, right? So then this is the multiplication from the left. In other words, omega tilde of x, y is simply t times omega times t to the minus 1. And now we need to relate these terms to the capital T. Yeah, that's better, yeah. Okay, so then that's what you suggest. Yes, now T flips exactly. Indeed. Okay, then we have that, and then we need to compare using this, right? And in order to get to the T, we need to apply the phi to it, the capital phi, to this equation. Because then this is what we get. So if I apply capital phi p to this, tilde, then this is phi p to the sum, and phi p is linear, so I can write this as sum phi p of xj of p. And this is then what I get when I apply phi p to this, which is this, simply this one, right? That's what you suggest. J. And here have this on the other side, so that's Tp of the I. Yes, so finally. So that shows us that this is indeed the representing matrix of the T in the standard basis. It's a representing matrix of T, P in the standard basis, and that means I can insert this here, so it's the same as a little t. Yes, good. But so note that these things are matrices with values in the Lie algebra, and this one, whereas this is a matrix with values in the Lie group. And in fact, this is called the adjoint action of the group on the algebra. Good. All right. So that's what we will need about curvatures and connections. And there's a last, pretty short preliminary part, which is of entirely algebraic nature. And this algebraic part is some remarks on the concept of polarization. So that's entirely algebraic. So we consider, so let K be R or C, or any field of characteristic 0 for that matter. And so let's look at two finite dimensional vector spaces. So let V and W be finite dimensional vector spaces. Now I want to say, what does it mean that a map from V to W is polynomial, or a polynomial of a certain degree? So a map P from V to W is called polynomial, or homogeneous polynomial of some degree, homogeneous of degree K. If, only if I choose a basis of V and I compose with the corresponding isomorphism of K to the N here, then I get something which is polynomial in the usual sense. So if for some basis E1 up to En of V, the map which goes from Kn to first V and then to W, so this composition where this is my P, and that's the isomorphism corresponding to the basis. So that's the isomorphism induced by this basis, so that means it's the map that maps the vector V1 up to Vn to, and then this maps this vector to the corresponding linear combination for these basis vectors, some Vr Vi. So that's an element here, and then I apply P. So this gives me a map on Kn of these n variables with values in a fixed vector space, and I suppose that I assume that this is a polynomial with coefficients in W. So this, if for some basis blah blah, the map is a polynomial homogeneous of degree K. We want to look at that case, homogeneous of degree K. With coefficients in W. So in polynomials. So for polynomial, this means it's contained in the set of polynomials with coefficients in W of the variables. I prefer to call this T1 up to Tn, okay? These coefficients that appear up here, and then I can write T1 up to Tn. Which would be the same thing as an element of the usual polynomials. Tensor is W. So it's a polynomial, but the coefficients are vectors in W. I could also insert a second basis on W and then look at the coefficients of those basis vectors, and then they would give me usual polynomials in these variables. That's what it means. And if this is true for some basis, then it's true for any basis. And hence, any basis, because it just change of basis just means you pre-compose with an invertible matrix here, and if you do this with a polynomial of some degree, then this gives you a polynomial of the same degree. Good. So these are polynomial maps, and polarization is something we know from degree 2, when we have polynomials of second degree, which can then be polarized to come from bilinear form. And the same thing can be done in any degree. So that's really the point I want to make here. Okay, how does this work? Well, how can we get such polynomials? One way to get them is start with a multilinear map. So if mu from V from k times to W is multilinear and totally symmetric. Meaning the order of the arguments is irrelevant, right? So it doesn't matter which order you insert the arguments. Then I can get such a polynomial homogeneous of degree k by just defining the corresponding polynomial to be this multilinear form where I insert the same vector k times. Then this yields a polynomial map in fact one which is homogeneous of degree k. Right? And now the claim is all polynomial maps homogeneous of degree k are of this form. So they all come from such a multilinear map. So lemma to each polynomial map P from V to W, homogeneous of degree k. There exists a unique multilinear, totally symmetric multilinear form mu with k entries such that P equals P. So there's really, you can go forth and back. So it doesn't really matter whether you talk about polynomials, homogeneous of degree k, or these totally symmetric multilinear forms. And why is that? This prescription here that takes a multilinear form, totally symmetric, and gives me a polynomial. So the map mu is being mapped to p mu. So that's a map from the space of all these multilinear forms, totally symmetric multilinear forms. To the map of polynomial maps. From V to W, homogeneous of degree K. And it's not just some map, it's a linear map. Because if you replace mu by linear combination, then you get the corresponding linear combination of this polynomial, this definition. Good. And now I claim that this map is in fact injective. And why is that? That's the proof. Well, how can we recover the mu from the corresponding polynomial? It can be done as follows. Let's look at, so fix the vectors v1 up to vn, k, sorry, these are k vectors. And we want to reconstruct this multilinear form applied to these vectors from this polynomial. And how do we do that? Well, let's insert the following vector into the polynomial, namely, let's take a linear combination of those. Okay, and let's differentiate it with respect to these coefficients. Now, what would you get? So, by definition, we have now to take the multilinear form, and this is our vector v, is this linear combination here. Okay. So, this is mu, and then we have t1, v1, up to t, vk, inserted k times. And now this is multilinear, so it's linear in each slot. So when you evaluate this and the v's are fixed, then this becomes a polynomial in the t's. And it's in fact a polynomial of degree, a homogeneous of degree k. And now so each term that I get by expanding this by linearity in all the terms here, each term that I get is homogeneous of degree k in the t's. Because I have k slots here, and I take one term from each slot, so this gives me always one t factor. So I will always get k t factors. And then I differentiate k times. And the only terms that survive, if you do this, are the ones where you take a different t from each slot. Because if you take the same t at two of the slots, then one of the t's is missing, and then you differentiate with respect to that t and you get 0. So really, you get this differentiation thing, selects out all those terms that you get by selecting a different t in each slot. And what will this give me? Well, this will then give me so if I do that and differentiate, then I will have, for example, mu of v1 here, v2 here, and so on, and up to vk here, or in some other order. I could have mu of v5 here, mu of v1 here, and so on, and to some other order. but by assumption mu is totally symmetric, so this will always give me the same thing. So the term that I get here, the coefficient of t1 all the way up to tk in this polynomial, as a polynomial in k, is exactly mu of v1 up to vk, except that it appears many times, not just once. How many times does it appear? K factorial, yes. Because it's all possible orders correspond to all possible permutations on k entries, so which is, there are k factorial, many of them. So that's what we get. And so we see we can reconstruct this multilinear form from the corresponding polynomial. So the multilinear form is uniquely determined by the corresponding polynomial, provided we are working on a field of characteristic 0 so that we can divide by k factorial. Okay. Yeah, in fact, for example, on the field of characteristic 2, this is not correct. And so what this shows, this thing is determined by that thing. In particular, if the p mu is 0, then the mu must be 0. So that means that this map up here is injective. It is injective, this map, because, and then we have this argument. So we have an injective map here. And now, in order to see that's actually an isomorphism, you can count dimensions. And this here, both spaces. So if I call this the multilinear forms, the space of multilinear forms, and this is the space of polynomials of degree k each, then both spaces xk mod, totally symmetric multilinear and total polynomials homogeneous of degree k, they have the dimension. What's the dimension? It's n is the dimension of the space here, so that is dimension of v minus 1 plus k on the dimension of v. So this would give the case when this is one-dimensional, and then I have to multiply by the dimension of w. With the exercise to check this. And so since they have the same dimensions, the injective linear map is an isomorphism. Therefore, the map is an isomorphism. Which proves this lemma, right? So that it doesn't matter whether I talk about totally symmetric multilinear forms or about homogeneous maps. And it's nice to go forth and back. Thanks for your attention.